In this video, we're going to continue talking about reaction mechanisms. And when you have a reaction mechanism, we know that we have the step 1, step 2, step 3. And in each of those steps, again, we call those steps the elementary step. Okay, each step, step 1 is an elementary step, step 2 is an elementary step. We're going to get into a little bit more detail with that here in a couple more videos, okay? But for now, just understand that each elementary step in a chemical reaction, again, is actually showing what's happening. Now, just like when you have a chain with a whole bunch of links in it, we know that the chain is only as strong as what we call the weakest link. Okay, well, think about a reaction mechanism. You've got, let's say, 4 different reactions. And in those 4 different reactions, one of those elementary steps goes slower than the other 3. Okay, and what we do is we call that the slow step, okay, or we refer to it as, more importantly, the rate determining step, okay? And just like the weakest link in a chain, a reaction is only as fast as its slowest step. Okay, so if they give you a list of 3 or 4 elementary steps in a reaction mechanism, how do you know which one's the slow step? Normally, they're just going to tell you. It'll literally be written right next to the chemical equation. Okay, looking at example 2 above, coming back to here, we could see that, or example 3, it doesn't matter. Very likely they may say something like fast, slow, fast. Okay, and there can only be one slow step because there might be some other slow steps as well, but when they talk about the slow step, they're talking about the slowest of all of the steps. This step is the slowest, and again, that is the one step that determines how fast the overall reaction is going to go. So why does it matter which step is the slow step? Well, we learned earlier in this unit that when you're determining the order of a reactant in a chemical reaction, we said you can't use the stoichiometry of the balanced equation. Okay, remember, if you have 2A plus 3B making 2C, whatever, you can't say, oh, well, the rate law is the rate equals K times the concentration of A to the second power. You can't do that. We know that you cannot use the coefficients in the balanced equation to determine the order of the reactants. However, the order of each reactant and the overall rate law can be determined using the stoichiometry of the balanced equation of the slow step in the reaction mechanism. Okay, so the coefficient of each reactant that appears in the slow step is the order of that reactant, and all of the reactants in the slow step will make up the overall, because remember, the slow step is what determines how fast the reaction goes, because it's the slowest of all of the steps. So the reactants in the slow step are the ones that go into the rate law. And only when you have a reaction mechanism and you know which one's a slow step, then you can use the stoichiometry of the balanced equation to determine the order of those reactants. Okay, sometimes the stoichiometric numbers will be the same in that slow elementary step as in the overall equation, but if it does, that's just a coincidence, and generally that isn't the case. Okay, so for the chemical reaction, example 1, the chemical reaction W plus Y makes Z has the following sequence of elementary steps, which means it has the following reaction mechanism. So step 1 is W becoming R, step 2, blah, blah, blah. So some of the things we could do here is we could identify intermediates and catalysts. It doesn't ask us to. Well, maybe not yet. Maybe it does. Nope, it doesn't. Okay, but clearly we can see that R is an intermediate, Q is an intermediate, and again, the overall equation would be W plus Y making Z. Wait, why are you writing that down? They're not asking us this. I know, I'm just reviewing, okay? Calm down. Okay, now they are saying determine the overall order of the reaction. So again, when they give you a reaction mechanism, you go to the slow step. And in the slow step, you look at that reactant. There's W, and there's only one W. Okay, if there was a 2 right here, then that would be, obviously, then it would be second order. If there's a 3 there, it would be third order, etc. But there's only one. Okay, so the overall order of the reaction is therefore going to just be first order. Notice I didn't even look at this overall equation, okay? Because I don't care. The rate law and the overall order of the reaction is based on the slow step. And that slow step only has W in it, and it only has one of them. So therefore, it is a first order reaction because W is first order. Okay, and so the rate law would be rate equals K times the concentration of just W raised to the first power. Okay, and there I just explained that again with the italicized K there. You like that, don't you? Okay, example 2. Step 1 shows A reacting with 2B making C, and then C reacting with D to make E and F. So again, even though it doesn't ask for it, let's go ahead and look for intermediates and catalysts. So I don't see anything that we start with also ending with. So I don't see any catalyst in here at all, but I do see that we produce C and then we use it again. So C is definitely an intermediate, which means in our overall equation, we're not going to see it in there at all. So in our overall equation, we're going to have A plus 2B, and the C, this C is going to cancel with that C. So plus D, those are all of our reactants, making E plus F. And they like using this using fake elements on the real AP test just because it makes it much, much easier for them to write questions. So don't be surprised when you see them. Okay, and then the rate law for the reaction is rate equals K. Every rate law starts out like that. Rate equals K times. Now, if this reaction, and it's not, zero order, can you have a rate law that's just rate equals K? Of course, if it's zero order and none of the concentrations affect the rate, then sure, that right there is a zero order reaction where rate equals K. All right, so now we go to the slow step. What do we do with the fast step? Nothing. When we're determining the rate law, we don't even look at the fast steps at all. Okay, we just look at the slow steps. So rate equals K times the concentration of A times the concentration of B. And again, remember, this is the one time, not only can you use the stoichiometry of the balanced equation, you must use the stoichiometry of the balanced equation. So concentration of B, and that is a second order. B is second order. So A is first order, B is second order. What is the order of the reaction overall? Overall, this is absolutely a third order reaction. And again, why? Because first order plus second order makes third order. Okay? So, let's review here real quickly. Make sure that when you're giving a reaction mechanism, they may tell you which step is the slow step. And when you know that, that is the step that you use to determine the rate law, and you do use the stoichiometry of the balanced equation to write that rate law and to determine the overall order of the reaction. Okay, there may be times where they may not give you this, but they might give you the rate law. They might give you this and say, which step is the slow step? And you go, well, the only thing that's in there is W, and it's raised. So, oh, well, the only place you find W is here. So which step is the slow step? Absolutely step number 1 is the slow step. Okay, so they typically do this. They give you which is the slow step and which ones are the fast steps. But if they don't, and they ask you to find the slow step, well, then you have to have some type of rate law that you can use and go back to those steps and try to figure out, okay, which of those steps would give me this rate law right here? And whichever step that is, that's the step that must be the slow step.